Today's our last lecture. We're going to do some second order practice after we learned about Bode plots, transmissibility, and then vibration frequencies at the end. We're going to do this problem together. I've had students before in the past do it on their own, and it took a while. So we're going to try this out. This is called shaker table. Now in dynamics in the lab, I think that maybe you did something with a shaker table, unscrewing like a bolt, aluminum, something like that. I'm not exactly sure, but we can see that, yeah, as we set up a shaker table, you know, if I change the frequency, I'm going to get different outputs. If I change the orientation, I'm going to get different outputs. So we have this shaker table, and we have a rigid connection. We have some kind of vibration mount. Now, this could be just like a rubber spacer, something like that. It has stiffness, it has damping, and it's connected to a mass. And our goal, what is our goal? If I know the input of the shaker table or the base has a input of 0.5 centimeters, that's the amplitude, sine omega t, and we can change that frequency. Based on the input, we want to find the values for B and K. Now, most of the time for like rubber, especially if you're buying it off McMaster, you can find the stiffness pretty well. Now, you can look up that. Stiffness is a really easy thing to check. You just throw weight on it and see how much it deflects. But we've talked before that damping is a much harder thing to find. So this is another type of test, not looking at from the time domain standpoint, but from a frequency domain. As I change the frequency, can I solve for B and K? So our goal is to find B and K. We're going to plug them into MATLAB once I have that transfer function, and we can test it. So we're going to use MATLAB today at the end of this problem. We're going to do a couple other problems as well. But let's look at the test data. And then I'll ask you, how should we go about solving this? So at a very low frequency, at 5 radians per second, the amplitude is 0.507 centimeters. Okay, so that means that the output is pretty close to the input. It's actually slightly higher. At 30 radians per second, I actually see a larger output. So that mass of 1.4 kilograms is going to have a higher amplitude of 0.7 centimeters. And then as we go to higher frequencies, we see that that drops significantly. Okay, so I know it's been a few days. Any ideas of how we could solve for B and K? Have it your way. What I have on here? Don't have anything. Oh no. Slides are getting sticky. There it is. Here's our problem. Let's see. We know that the input is constant, but as far as the amplitude, and then as we change the frequency, the output changes. Our goal is to find B and K that will give us those kind of outputs. Any starting point you can think of. How about this? Right now, do I have an equation with B and K yet? No, I don't. So let's find the transfer function. remember that for this topic, everything comes out of the transfer function. So if I'm not given a transfer function, that's the first thing I should find. So we're going to do both body. We're going to get to the transfer function. Then from there, we got to figure out how are we going to use this data to try to solve for some of our unknowns. All right, so let's go for it. So here's full body. First off, let's take a breath. Capstone tomorrow. Wow. Okay. But it'll be done. Well, no, it won't be, because then you have other presentations for some reason. Okay. Order. What's the order of the system? Second order, I have one mass that we can track that has motion. I'm getting ahead of myself. Here's the body diagram. Now, just like with most things, if I have a shaker table and I put the mass on here, the spring or the material will deflect a little bit, but we're going to consider it to be in equilibrium. So before I turn the shaker table on, everything's in equilibrium. I do not have to include mg. But which way should these forces point for K and B? They're in parallel, so I'm going to have them face the same way. Should they point up? Should they point down? Okay, we have one for up, one for down. What do you think? Two down? Is he up or down? You're gonna. Oh, it could be either. Yeah, absolutely. So let's see. To match my notes, to make this, it's not like it's easier. I'm just picking one way, but I'm gonna say that XB, that the base first moves positively, compressing the spring. So if it moves up, spring compresses a little bit, it's going to push up on the mass. But yes, it could go either way because it is between 2 points that can move. Right? Both ends have a freedom to them. So there will be a delta involved here. Now the input is obviously the base motion and the output is the position of the mass. Okay. So we're getting closer. Now we got to get all of the definitions. Like I talked about, these are tied between 2 points that can move. So for both of these, I need to have a delta. So I'm going to get my definitions going. This is going to be K delta X. And then for the damper, it's going to be B delta X dot. And what should our delta X turn into? By the way, this should never be in the final equation. You should never have a delta in your final equations. I've seen it sometimes. What minus what? Yeah, it should be the greater minus the lesser, just to match our free body diagram. So therefore, if I'm saying XB is greater than X, that gives me a positive value. Means it will be pushing up on the mass. And then the same thing here, we're just dealing with velocity. So it's going to have a position, it's going to have a velocity. We're saying the base is greater than the mass. Okay, what do you think? Okay? All right, so next up, we're going to do sum of forces. equals mx double dot. I have two forces, and they're both positive. So we're just going to put their definitions in here. Now we're going to bring all of the x's. These are both negative. That's good. We're going to add them to this side, and we get mx double dot plus bx dot plus kx equals bxb dot plus kxb. So we do have one stable second order equation where xb, the base, is the input, and x is the output. So what should the transfer function, what will the transfer function be? You want to tell me what the transfer function is? Huh. You're already doing it. So, what? Output over input? It's on the numerator. Well, actually, that's going to be the denominator. We should have a bs plus k numerator over ms squared plus bs plus k denominator. And we do know the mass. It doesn't say it on here, but if I flip back a page, m is equal to 1.4 kilograms. So we can plug that in. So the mass is pretty easy to find. But again, we have some material, maybe some kind of rubber spacer or something that has a stiffness and damping that's really hard for us to determine. And so that's our next step, is taking this transfer function and trying to, based on the frequency and the outputs that we see, determine what B and K are. Okay, so now we have the transfer function. So we have a couple options. The first option is I put this in MATLAB and I just plug in random values until we maybe see something. I give it a sinusoidal input and we just kind of run with it and see if it works. So I might be able to match the first one after 20 minutes, and then after that it probably wouldn't match the other one, so I'd have to adjust it more. What is another way we could possibly solve for B and K? Did we do anything with frequency and amplitude last week? Very good. Yeah. So we talked about the sinusoidal transfer function. So that's going to change as omega changes. So if we do S is to omega I as we create the sinusoidal transfer function. So that would be like B omega I plus K over 1.4 omega I squared plus B omega I plus K. So this would be our sinusoidal transfer function, which does, like, at different frequencies, we do see that these values change. So from there, we can try to calculate magnitude and phase, and we are looking at magnitude in this case. Now, again, what I've always pointed to with these is trying to get it into a simpler form where we just have one imaginary term and one real term on both the top and the bottom. So what is I squared? -1. So that the I goes away on here. So I can combine that with my K. That's part of my real term. So this would be B omega I plus K minus 1.4 omega squared. Okay. Now we have a sinusoidal transfer function. We have two unknowns, B and K, but I've done some testing. I know that based on these different frequencies, I get a different output amplitude. So we're going to go to the next slide because I'm running out of space here. But what we want to find is, first off, what is my actual amplitude ratio here? And from that, can we actually determine B and K? We're going to have to run it a couple times. I can't solve this with just one equation. I have two unknowns. So we're going to have to solve it with a couple other frequencies. That's why we've got the table. But before I go to the next page, any questions? Okay. So first off, I need to figure out the amplitude ratio. So this amplitude ratio is just output over input. And the problem did say that XB, the input is 0.5 sine omega t. And so the input is 0.5 centimeters. The output we get at low frequency is about the same, 0.507. We see it jump up here, then it drops. So we can calculate first amplitude ratio. This is just output X over XB, amplitude. So this is 1.01, 1.4, 0.995, and then 0.506. That's the same thing as magnitude. Amplitude ratio, magnitude, same thing. Okay? So here's how we would solve this. And this is not an easy problem. This is I just want to say this is harder than what you have on the homework. All right? Because there's a lot of algebra in here. But it's kind of a weird way to take test data and try to work our way back instead of knowing some of those values and finding the Bodie plot, let's say. So let's look at the first one. I have a frequency of 5, and then my amplitude ratio is 1.014. So the magnitude or amplitude ratio is equal to 1.014. This is equal to what's here up at the top. This is our magnitude at 5i. So we have a frequency of 5. And I would just plug this in. So we have k squared plus this would be 5b squared. So this is from the top equation right there. I'm plugging in 5 for omega. And then this would be k, one of our unknowns, times 1.4 times 5 squared. All of this gets squared. Then we have 5b squared again. So again, this is our equation for this transfer function. It takes the sinusoidal transfer function. Now we're finding the magnitude of the top divided by the magnitude of the bottom. This changes based on what omega is. So that's what we're using to be able to solve for B and K. And so we can simplify this a little bit. This is K squared plus 25B squared. And this part would be K minus 35. All of that is squared plus 25B squared. So now we know what the left-hand side is equal to. Because of our testing, we know the amplitude ratio is 1.014. Now what I have to do is I have to kind of take this over here. Maybe I square it. I just try to get an equation, because once I get one equation, I'm going to do the same thing at different frequencies until we have enough sets of equations to solve for the unknowns. So, for example, we could change this to become K squared plus 25B squared is equal to 1.014 squared times K minus 35 squared plus 25B squared. And we could work this out a little bit. Okay. Again, this problem is a little bit harder than what you got to do on the homework, but we're taking this magnitude that we know, we're trying to find these unknowns, and so we can rearrange it. You know, we can multiply, we can square both sides, multiply this over here, kind of work that out. So I can still work this out a little bit. And now I've got one equation that has a b squared, it has a k squared, and it has a k. So this would be equation 1. And just like we've used before with our partial fractions for Laplace transforms, we can use our calculator. Once we have it set up all the same form, we can use our calculator, set up that system of equations, and be able to solve. That's our starting point here. Before I do some of the other ones, questions about what's going on here, using the table. Any questions about the setup, which is based on the transfer function? Again, stiffness is pretty easy to find from a test. Damping coefficient is not. And so having a test where we can change the frequency, we can change the magnitude effectively, and from there we can calculate what that B and K values should be. So we would do the next one. So at 30, so for part 2, this would be the magnitude at 30I is equal to 1.402. So our amplitude jumps up quite a bit at that frequency. This is probably close to the resonant frequency. Again, the Bode plot is all based on this amplitude ratio. So it jumps up, we're probably close to resonance. I've got that large output, and I'm going to use that same equation up at the top. It's going to be k squared plus, now I'm going to have 30b squared. We're going to have k minus 1.4 times 30 squared. All of that is squared, and then again we have a 30b squared. So it's pretty time consuming. Obviously, I could do it in Excel, maybe set up that equation and be able to solve this a little bit easier. But this can change to, let's see, we got k squared plus 900 b squared. And then we would have k minus 1260 squared plus 900 b squared. So we can get to a second equation, which would be k squared plus 900b squared equals 1.4016 squared times k squared minus 2520k plus 1,587,600 plus 900 b squared. Good. Now, to save us from a little bit of carpal tunnel, okay? Already at 7 in the morning. We would do the same process. Now, really, I have essentially two unknowns. I just have k and b. What may help, though, is to have three equations, because if you're looking at here, I've got a b squared term, I have a k term, and I have a k squared. So we could solve it with two equations, but it may be easier to do it with three. So we would do the same thing. I'm not going to write it all out, but I would take that 60 radians per second. I know that the magnitude is 0.995. That's output amplitude over input amplitude. And then from there, we plug in 60 for omega, and we get a similar looking equation. Notice these numbers jumped up quite a bit, right? So as that omega changes, I get a really large change in that equation. But we'd be able to solve for k and b. And that was our goal all along. And so then we would have three equations, three unknowns. And so you can set them up again. If you write them all out, you get some kind of b squared, some kind of k squared, some kind of k equals a number. And once we have those three equations, we can use our calculator to solve for those unknowns. So I'm going to write those up here. If you can pull out MATLAB, we're going to use that soon, because we're going to see, can we get a similar transfer function that actually gives us outputs that make sense. So for your homework, you're definitely going to want to, well, some of it's required, but using MATLAB to kind of back up your answer. Oh, I get this answer, and Simulink can actually get something close, or MATLAB. You can always double check some of these things. Questions about this? Okay. Let's see. All right, so I'm going to take these three equations. I'm not going to expand them all out and finish it out, but once I have those three, we would find these values. So k squared is equal to 6.24 times 10 to the 6th. K is equal to 2,500. This would be newtons per meter. And then B squared, I'd get 3729.4 newton seconds per meter. So therefore, B would be equal to 61.07 newton seconds per meter. So by running those three equations, we could solve for this. It's just based on experimental data. And therefore, my transfer function would be 61.07 s plus 2,500 over 1.4 s squared plus 61.07 s plus 2,500. So we found a B value, we found a K value, and then for our equation, which was just BS plus K over MS squared plus BS plus K. Now we have those two values that we can plug in there. Oh, we can. What I want you to get from this, I know the math is a little bit difficult understanding it right now, but this is what a lot of engineers use. Anytime you have like an unbalanced rotation, you have something with an oscillating output. Actually, one student that was just in this classroom a year ago just finished some training for his company that he works at for vibration analysis. So vibration, resonance, it's all based on frequency. As I change my input frequency, how does my output change? From that, we can actually create a model for the system. It could be a really complicated system, but based on the frequencies that we see and amplitudes at those different frequencies, we can create a model of how this is going to work. And then from there, we can try to figure out what the ideal operating frequency should be. Like, how fast should this be spinning? What I want you to do is take this transfer function and create a Bodie plot. So we should have the code up. We used it last time in class. But you're going to create your transfer function. This is numerator, denominator. And from there, we can create a Bodie plot. Do we get something similar to what we see here? Because this was a lot of math. We could have made some mistakes, some algebra mistakes. So I'd like you to plug this in. Remember, it only takes basically 4 lines of code. Numerator, denominator, system, transfer function, Bodie of that system. Once you have it defined. Honestly, you can do it in 1 line of code. That is possible. Kind of do all the steps in one. Yeah. Okay, so you put it in brackets. You put bracket 61.07 space 2,500. That would be your numerator. By the way, what is the DC gain of this transfer function? It is 1. If all the s's go to 0, I'm left with this over that. That's 1. So the DC gain which it means that's at our low frequencies. At low frequencies, the output basically matches the input. That's what we see here. So K should be equal to 1, which means our starting point, 20 log of 1 equals 0. our Bodhi plot should start at 0 decibels. And then you're going to see a bump. That's going to be close to 30 radians per second. And then it goes down after that. So you need to have practice, like you have for the denominator. Anyone get one yet? Working on it? Oh no. Update. The right timing. Man. You got a Bodhi? You got a Bodhi. Okay. Wow, so yeah, our peak actually looks maybe a little bit closer to 40 radians per second instead of 30. Yeah. That looks good. Yeah. So again, we talked about DC gain is 1. So therefore, our starting point for the Bodhi plot should be 20 log of K. K is 1, 20 log of 1 is 0. So 0 decibels is the starting point. We should see a bump. And what is the peak at? I think I've got it up here. So at 30 radians per second, or close to 30, we have a magnitude of 3.13. Decibels, again, we start at 0 and then it tails down. So we can kind of compare this. Looking at this, maybe, I think this is 10, 20, 30, 40. Our peak might be closer to 40. So we can actually, even though I only tested a few frequencies, from those frequencies, I'm able to create this transfer function, which creates the Bodhi plot. We can actually figure out, like, what is that maximum value? What is the resonant frequency? And typically, we're trying to avoid those frequencies. I don't want to run this at resonance. If I'm at resonance, things start to shake. They start to fall apart. And so I can figure out, like, maybe I'm okay with the magnitude the same as the input, or maybe I want to run it higher than 100 radians per second or something like that. So that's how we can check it. And then what you can also do is, if I'm purchasing different types of material, how does that B value change it? If I change the damping to something like 40, what happens to the graph? Well, I think my peak will go higher. I might shift to the left or right. So depending on your material, if I have to make a quick material change, I can do that like this, plug in a different material and see how that changes my frequency graph. So, like the MATLAB guy talked about last time on the video, looking at everything in the time domain is like it's helpful. It gives you some stuff, but frequency domain is like, especially for anything with an oscillating input or rotating, right? And it's unbalanced, and I get some kind of, looking at it from the frequency domain, we can really see what's going on. As I change frequency, how does that affect my output? Questions? Is anyone outside tomorrow for the showcase? Oh, you are. But you are too? Ah, the vending, yeah. You can't really direct. You can't have a vending machine in a building. Cool. I got a group too. What? The back, yeah, somewhere. It's like, just put it at least in the shade, like right outside. Oh, you're under the tree? Oh, that's nice. I don't think any of my groups are under the tree. And people are gonna actually come by with their bikes and like. All right, let's we'll cover the transmissibility and then we'll I believe take a break. We'll see. What we just talked about, like with the shaker table, we were able to create a Bodhi plot. We can find the resonant frequency. That frequency can kind of account for vibrations. So vibrations are typically undesirable. Why do we want vibrations? Why don't we want things like hitting their resonance? It breaks. Like, think about this. Have you seen those videos where like opera singers, they sing and you got this like glass, nice wine glass, and you sing and you hit that right frequency? What happens? Well, that resonance, it's hitting the right resonance for it to, like, honestly, everything starts shaking until it breaks, right? And so we see that even with suspension systems, everything like that. We don't want to hit resonance. We don't want that because things can fall apart. So typically we want some kind of suspension to try to isolate the body to damp out any kind of vibrations. So we have vibration isolation systems to reduce the transmission vibrations two different ways. Either I care about protecting the machine, so trying to dampen out any vibrations that could affect the machine, or my machine has a lot of vibrations, I'm trying to prevent them from getting to the floor. All right. So just as a quick example, if I have some kind of instrument, you can think about this as, I mean, if you're doing quality control, you might have a lab where you've got all the important test equipment. Downstairs on the first floor, you took materials lab. You've got all that different test equipment. Some of it's very specialized. You want to make sure that it's not affected by anything transmitted by the floor. So what they have typically is they have rubber feet, some kind of vibration mount to avoid any kind of large displacements or vibrations at certain frequencies for the system. So we can represent that with just a spring and a damper. I'm giving it, again, some kind of rubber mounting, typically, which has a B value, it has a K value, and so from there we can dampen out some of those different vibrations. The goal is to reduce, try to take this and then make that amplitude pretty small as well as we can. So that's all based on frequency. What kind of frequencies do we see? I want to give you some quick examples. Last semester, I actually found these in the capstone area. I think there was a group trying to make a vibration damping table. And so what they found was they found these nice, these are rubber, but they're also filled with air. And so these are some like heavy duty mounts to make sure that we have some separation, the table from the floor. So you can increase the air or you can decrease the air to change the effective mass, the effective spring constant. And so if you know what those frequencies are, you can try to tune those dampers to be able to get the amplitude you want. So trying to avoid any high amplitude. Have you used this before? It's right next across the hall. This is the SEM, scanning electron microscope. It worked good for you. You did the materials lab. You could look at stuff, butterfly wings and stuff. No, microchips. It's kind of crazy. It's like a tiny city in there. It's nuts. So a few years ago, students couldn't use this. You know why? A crack had started forming inside this very specialized heavy duty. Why did a crack form? We didn't know. Now, this company does sell vibration damping mounts for this machine. Did GCU purchase the vibration damping mount? No, they did not. Because they thought, it's a lot of money. Why do we need that? We'll just put it on the second floor. Now, most of our specialized equipment is on the first floor. You know why? Because it doesn't move that much. Second floor, though, you have people walking by. You have things rolling. through the hallway. With all that footsteps, what happens is that even though it's concrete, right, we can still create frequencies. And from those frequencies, even small, they don't have to be large amplitude. They can be very small amplitude, but it's based on the frequency. Like the guy talking about the rumble strips last week, right? They don't have to be very tall, but it's the frequency that over time, with all these different frequencies coming through, those frequencies can affect the system. And that's why it cracked here, and they had to get it fixed, which was also expensive, right? So we have to understand that, over time, small things can add up, small frequencies. If it hits close to like the resonant frequency of one of these very specialized components within here, that can cause problems. So that's why having a mount is very helpful if you want to protect what's going on, or at least put it on the first floor. So transmissibility is kind of the name for suppressing vibrations. We can look at it two different ways. So transmissibility can look at the transmitted displacement amplitude, or it can be about the force. Both of them are correct. So either I'm transmitting a force or a displacement. Transmissibility is kind of the word of, I have this input, and this is what the output's going to be. Now, for a mass spring damper system, so transmissibility is mostly, we don't talk about it for circuits, we don't talk about it for hydraulic systems, whatever. Transmissibility is really just mechanical, where I have this object, I have some kind of mount for it, but transmissibility is the same thing as the amplitude ratio, right? If I have the floor that's has some vibrations, I want to make sure that my mount protects the machine. Now, the other way around, this works for the other way. Let's say I have a washing machine or a clothes dryer. Why do they have rubber feet? Have you ever moved one of those things and the feet came off and you're just like, I'm just going to leave it without any feet? You feel that throughout the whole house, right? So the goal of those feet is to reduce the transmission of those vibrations of the machine to the floor. And so that's all based on a B and a K value. That's what those dampers provide. So from that, we can dampen out different frequencies. So we can look at it either from a displacement standpoint or a force. Looking at force. Okay. So transmissibility is same thing as magnitude. It's just for a mass spring damper system. You don't really have to write this down. We just did this problem. So we came up with our transfer function, right? It was Bs plus K over Ms squared plus Bs plus K. So if I put it in the standard form, I divide everything by mass. It looks like this. And you don't have to write this down. But if I start there, then from there, because I know it's a sinusoidal input, we can create the sinusoidal transfer function. We can make some substitutions. So we know that I can change the standard form to be in terms of natural frequency, damping ratio, stuff like that. And then we get to this equation right here. This is on the equation sheet. This is transmissibility. It is the same thing as the amplitude ratio. So I have my system like this. It's really just for this sort of mass spring damper setup. But this is my transmissibility equation, second order. And let's talk about beta. Beta is the frequency, the operating frequency over the natural frequency. We know that every system has a natural frequency. So this is close to the resonant frequency. It's the natural harmonics of the system. So if I'm close to that, if beta is close to 1, that's where we're going to see the maximum transmissibility, where beta is close to 1. But as we go lower or go higher, we're going to see that this transmissibility goes down. It's very related to the Bode plots that we've been talking about. So again, this only works for a mass spring damper setup like this, relating frequency to amplitude. So I just want to point this out. You don't ever have to use this. You can always use the same sinusoidal transfer function, set it up that way to find the amplitude ratio, to set up the Bode plot, stuff like that. This is just a specialized equation for this sort of setup if I want to look at my frequency as a function of the natural frequency. So I'm going to show you some plots, and then we're going to take a break. But it's going to look very much like the Bode plot. So in the book, it goes on about transmissibility. So this is transmissibility on the left, or the y-axis. This is beta right here. So I was talking about if my frequency is close to the natural frequency, if beta is equal to 1, that's where we see the highest amplitude. I'm pretty close to that resonant frequency. If there's no damping, I have, like, my resonant frequency is my natural frequency. We have almost unlimited amplitude. As damping increases, that's where we see the resonant frequency shift a little bit, and then the bump goes down. So this is a damping ratio of 0.2. And then 0.5, we see it dampen out, and this is a damping ratio of 1. So we can look at it for a system, again, washing machine, whatever. What is that frequency? What's the operating frequency? Based on that, I can try to solve for what B and K should be, so we can limit some of that transmissibility. I can try to dampen out certain frequencies. So the two things going on is beta and the damping ratio. Transmissibility is equal to 1 at this point for all damping ratios. They all meet at that point, which is kind of interesting. When beta is very small, transmissibility is equal to 1 because K is equal to 1. And so at really small frequencies, if it's really slow, they're going to move at the same distance. But as that frequency increases, we see, we hit the bump. Anything over 1, we start to decrease. Let's see. And transmissibility is less than 1 only when beta is greater than square root of 2. So that's the point right here. So on the next page, as the designer, if I have this object and I want to, like your pool filter cleaner, is it going to shake? It's not going to shake. It's going to be fine. You've tested it. It doesn't shake at all. Okay. Well, for some capstone projects, right, you might have like a good amount of shaking. First off, you got to make sure your screws and everything are tight. But to try to avoid that, right, you have some kind of damping. So maybe you put rubber feet on it, whatever. For minimum transmitted force or motion, we want to choose vibration mounts with undamped natural frequency much lower than the expected input. What that means is if I have a really low natural frequency and I'm running at a higher one, that means beta is to the right. And so based on that, I should see a lot less transmission. So like for the SEM, that vibration mount has a low natural frequency. So therefore, all of these frequencies of the ground and everything like that should be damped out. Those are higher frequencies than the natural frequency. That's the goal here. And then selecting mounts with light damping. So actually with the lighter damping, if we're running up here, that's where we see the lowest transmission. If we have a lot of damping, we don't see as much of a change. It's kind of constant over a large range of frequencies. So that's just another way. This is basically a Bode plot. It's just not on a log scale. Beta is our x-axis, so it's just really a frequency ratio. But it's the same concept as the Bode plot. We still see that bump if we have low damping, and then we see it go under 0, just not on a log scale. Questions? Okay, so transmissibility is just for mass spring damper. Now frequency is kind of a tough thing because we've already talked about time domain. Maybe I really care about settling time. Well, settling time is related to B and K. But if I'm getting too much amplitude out at different frequencies, I have to change B and K. And so when I change those, maybe to make my transmissibility a little bit less, make it better for my system, dampen out some frequencies, now I change my settling time. And so there can be quite a balance of trying to take this information, time-based information, and then the frequency-based information and try to find the right mix for those. So that's where some of this balancing can be hard. Or maybe I can increase the mass. Maybe I should decrease the mass. Like we've got 3 basic components of the system. What can we change to get an outcome that works for both domains? All right, that was transmissibility. And let's take 5. So that'll be 8, like 09. We can come back. The last thing we're going to cover is vibration frequency, another important aspect of types of systems. All right, let's take 5. Oh, yeah. Well, well, just so everyone knows, homework 6, we're not doing. All right, 2 things due. It looks like it's homework 7. Homework. Yeah, well, that's. But homework 6 is kind of take points from all the other homework. But we, I've been telling them this all those extra points. So if you could do this, that's your policy. That is a lot. How many of those are capstone? Well, ugh. Yeah, for 2 credits hour. Now, I did last year. I did apply to teach capstone. I was really interested in doing that. So I did like some of the interviews and stuff. I wanted to make changes. Mostly, there's too many assignments. But then they called me and they're like, "How would you still be interested if it went from a 9-month position to a year-round position?" And I said, "Absolutely not." So that's why you guys that's right. Yeah. No. But yeah, I'd like to see some changes being made. Anyways, the last thing we got to cover today is vibration frequency. So this is the last thing when we're talking about frequency. We've talked about magnitude and over frequency range. What do we see? This is vibration. It's a little bit different than the rest. So vibration frequency. This is really just one page, and then we'll do some practice problems. But this is simply the complex portion of the poles of the transfer function. Bless you. So if I have my transfer function, I can find the roots or the poles. It is the imaginary part, the complex portion. So really easy to find. The system will vibrate at those frequencies after an impulse. So this is the only time where we're going to see it's not a sinusoidal input. I'm just hitting it. So with an impulse, what will those frequencies be? And this can also tell us about the system. Captain America's shield. What's it made out of? Vibranium. We can figure out some of the properties of that shield by hitting it with a bullet. That's an impulse. Bang. It vibrates. That's the vibration frequency. So this is the frequency that vibrates after an impulse. Let me give you another example. I just came across this a few years ago, and I think it's a great example. There are systems in this classroom that if you hit it with an impulse, you get oscillations, all right? So, for example, right here. Now, if I did that too many times, it might. Does this one work? I don't know. I usually use the center one. That one's pretty good. It's got a little bit more damping, I think. So, and that could be, you know, some of it's the connections. Obviously, we have materials, we have masses, there's connecting points. And so all of this system, we could model as like one large piece where if I hit it with an impulse, I get this vibration frequency. So we can kind of piece together a transfer function based on those roots. You know, part of it, we can also see like how long does it take for the system to die out. This one's got more damping. It doesn't die out. It dies out pretty fast. This one rotates for, it oscillates for a good amount of time. Kind of works its way through. So let's do a quick calculation real fast. If I have my transfer function, let's say, and an impulse is applied, what will its vibration frequencies be? I also want us to look at what are the differences. So first, I want you to find the vibration frequency based on this. And then we're going to compare them to the resonant frequency and the natural frequency. Because they're close, they're not the same. So you can use either the quadratic formula, you can use your calculator. The goal to find vibration frequencies is to find the roots. That's what you got to find. This is second order. We should have two roots. Typically, a system is under damped, so we're going to have complex roots. What? What are the roots? Perfect. Okay. Right now, me out. This was a transfer function. We just use quadratic formula or our calculator to find the roots of the polynomial, set the denominator equal to 0. We get -3. Now that tells us how fast the system will get back to steady state. So we would have like an e to the -3t sine 4.7t. That's basically what these roots tell us. That's going to be sine, cosine, something like that. But it dies out. So when I hit it with that impulse, it's going to oscillate at this vibration frequency. That's the oscillation. That's the frequency we've got. But it will die out. That's what the roots tell us. So once it's taken away, we're going to get back to 0 within a couple seconds. Now, I just want to show you, because this is different than the natural frequency and the resonant frequency. If I wanted to find the natural frequency, How would I go about doing that? What happened there? Natural frequency. All right, let's put it in standard form. So we have 0.25 over s squared plus 6s plus 125 divided by 4, 31.25. So this would be standard form. Now, how do we find the natural frequency? Very good. So natural frequency is square root of that final term. And so that would be 5.6 radians per second. So we can see that the vibration frequency is going to be a little bit less than the natural frequency. Okay. If I wanted to find the resonant frequency, I need to know what the damping ratio is. So to find that, now that I know the natural frequency, I know that this 6s is equal to 2 zeta natural frequency. So that's 5.6. So we can find the damping ratio should be 0.54. Then we can find the resonant frequency. Using our equation sheet, it's equal to natural frequency times the square root of 1 minus 2 zeta squared. And this would be 3.62 radians per second. So I just want you to take a look at this. Here's our natural frequency of the system. Here's our resonant frequency. This is where the peak amplitude will occur. If I hit that, if I give it a sinusoidal input, this is where we see the maximum output. But what I'm giving it is an impulse, and that frequency is kind of right in between the two. Right? So all three of these frequencies are going to be close together because that's kind of part of the natural, that's just the system, how it's made up, the components going on. The combination of those has a very similar kind of resonant, natural vibration frequency, so it's kind of nestled in between the two of them. Okay, so this is how you can find the vibration frequencies if we're giving it an impulse. What we see there, we're going to finish up with one last problem, and then we'll be done with lectures. Okay? Questions? Okay. So we have now uncovered everything. That's all we've done in this class. I guess we'll talk about it next time, but really for the final test, it's mathematical model transfer function. I just want to get to the transfer function. Everything comes out of the transfer function. Either I'm trying to find the frequency response at a given frequency. Maybe I'm trying to understand a Bode plot or trying to create a transfer function from a Bode plot, as well as vibration frequency. So I can get that from the transfer function. And just remember, transmissibility is the same as magnitude, same as this. It's just for a mass spring damper system. All right, our last one. Example 9.10, the laser disc system. Anyone have laser disc growing up? You had actual laser discs? They're not the same as DVDs. Were they pretty big? Wow, you actually had some laser discs. Wow, cool. So there's some of you with laser discs. This basically came out right before DVDs, and then once DVD came out, it kind of just made it obsolete. But my dad was really interested in it. He got a school grant for his school to get one. Then he got some Laserdisc videos, and after that, like the next year, no one had them anymore. So the Laserdisc. Now I'm not guessing. No one had a portable Walkman, right? Like a CD player. Yeah, that's a little late, right? But some of you might be retro. You may have had that. They all kind of operate the same, where you have this cart. And so I don't know if you've had a DVD, but typically there's like a cart that comes out, and then you put the disc on it, and the cart goes in. And so that cart has some rubber vibration mounts to it. There is a laser. So, well, this first spins the disc, and then there's a laser that reads the information, and that can move as well. Now, this is pretty complicated, right? I have a couple different materials going on. We can assume some things are frictionless, but it's a complicated system. Trying to figure out, like, if I bump this, how much will my laser feel that bump? Like, what kind of vibrations are we going to see? And so we're going to take this, we're going to simplify it. So right now it's pretty complicated, but this is the model that we'll be working with. So really simply, this is my cart. There's some vibration isolation mounts. There is a connection to the pickup head, which has the laser. And our goal is to figure out, for any kind of movement of the frame, what kind of movement are we going to see from the pickup head? So we're going to create the model. Our goal is to create a transfer function. We're going to determine the vibration frequencies, and we're also going to create the Bodhi plot. So we're going to see, for this system, what kind of frequencies may we not want to, like. So I had a portable CD player. It wasn't very good, but you really couldn't run with those things. You know why? Because if I'm giving it a sinusoidal input and there's not much damping, stiffness, this laser is just going all over the place. Can't really run with it, right? Unless you could run at a certain frequency. So once we have the Bodhi plot, we can kind of figure out what frequencies are okay, which ones are not okay. Can I put this on my washing machine? Would that mess it up? I don't know. So we'll do some calculation. Hey, you ready for some writing? Now, yeah, we're going to start with bow body. We've got to get to the transfer function. So I've got the model right here. Our goal is to get to the transfer function. Let's start with the first part of bow body. Take a breath. What is the order of the system? It is fourth order. Thank you. I have two second order equations, two different masses, each with 1 degree of freedom. That's what we're working with. And now we get to the body diagram. So this is going to be mass 2. This is going to be mass 1. So they say the chassis in the cart is mass 2, which correlates with x2. Now we got to put our forces in. All right. So let's start with K2. K2 right there between the frame and the chassis or the cart. Which way should that act on mass 2? This spring is attached to two things that can move. So the frame, that's kind of my input, X in, that's going to move. Is the spring in tension? Is it in compression? You want it in compression? Compression? You can just choose. You want to, yeah. What you want? You want it to be in tension, but you want it to push to the right? Let's say that X in is greater than X2 greater than X1. It's true, we can choose whatever direction we want, but when I get to my definitions, I just want to make sure that I am consistent. So let's say X in, that's what I start with. The frame moves positively. What happens to the spring? It compresses. So what does it do? It pushes it to the right. So we're going to say this is FK2. It's in compression. Anytime I have a spring and damper, I'm going to put them in the same direction. We can also think of that material is trying to slow the frame down, and at the same time, there's an equal and opposite force pushing on mass 2. Now, let's say that's happened. Now it's pushing mass 2. What's happening to K1? X2 goes positive. K1 is in compression. So now I got to have both forces. So it's going to be pushing back on that while also pushing this, equal and opposite, FK1. Same thing for FB1. Now there's no other friction. Anytime we have the wheels, that indicates frictionless. So those are our forces. Again, we could draw all these arrows the opposite way. That's totally fine. It just, for our definitions, we're going to say X in greater than X2, which is greater than X1. What's going on? Okay, input, output. And really, we got mass 1, mass 2. Mass 2, the input is going to be X in. That's causing it to move. What is the input for mass 1? Pickup head. X2, very good. Okay, that's pretty good. It's not fully complete, but we know that if I move X2, I'm going to get X1. If I move X in, I'm going to move X2, that chassis cart. Will that cart move based on any other input? And the answer is yes. If for some reason that pickup head moves, that's also going to affect X2. Okay, now we get to our definitions. So we're going to do FK1, FB1, FK2, FB2. all of these springs and dampers are deltas. They have two ends that have degree of freedom that can move. So this is going to be K delta X. This is going to be B delta X dot. For FK1, what should delta X be? This is the one between the two masses. Very good. We said that X2 is greater than X1, so we're going to be consistent with that. This gives us a positive value. And again, you can always check this at the end. If I don't have all positive on the output, that means I have an unstable system. I probably didn't match the definition to the free body diagram. What about FB1? Now we're dealing with velocities. Yeah. So now we got the difference. Again, same direction, same arrow direction. Gonna look like that. Let's move on to FK2. K2 times what minus what? Greater minus lesser. Yes, Xn minus X2. And then for the damper, same thing, but with velocities. All right. So we have our four definitions for our four different forces. We're going to take those and we're going to create our two second order equations. One set of one equation for each mass. So we can start with the easy one first, mass 1. So for mass 1, I just have two forces. I have a positive FK1 plus FB1. So we can just put those definitions out there. So there's my two equations. Use the definition. And now we can get all the x1s together. So thankfully everything adds up. It looks good. We have m1 x1 double dot plus b1 x1 dot plus k1 x1 is equal to b1 x2 dot plus k1 x2. That is our first equation. And I could create a transfer function from that. I'm going to leave it as is for now, but we can create a transfer function. And the reason why, again, I've talked about this before, I always put the highest order derivative first. So both for the left and the right hand side. This is the input, the output, second order equation. All right, that looks a lot like the one we started class with, didn't it? It was just a flip, but it had a moving, and it had a spring and a damper. Great. Okay, now we're going to move on to 2, which has 4 different forces. So it's going to be a little bit more complicated. We do sum of forces equals M2 X2 double dot. We have a positive FK2 and FB2. And then we have negative 1s. So now we put our definitions in. And then again, we can check before we do this, all of the X2s are negative. Good for us. That means we're going to add them all to the other side. So we get M2 X2 double dot. Now I have both a B1 and a B2, so we're going to combine those. B1 plus B2 times X2 dot. And I have a K1 and a K2. And then we have B2XN dot plus K2XN plus B1X2 dot, no wait, X1 dot. Plus K1X1. Okay, so I have my two equations. Again, stable, second order, total fourth order. We know that X2 is affected by both Xn and X1, so those are my two inputs here. Whereas X1, that mass is just affected by X2. So single input, single output. Now, our goal here is to figure out the vibration frequencies for this, which means we need to come up with a transfer function for the whole thing. I have this equation, I have this equation. This one I can create a transfer function for. This one I have two inputs, so it doesn't quite work. Okay? So how can we, what can we do with this? Okay. First off, let me just draw this out a little bit. I have this system. What happens if we looked at it from like a transfer function, this sort of way, or sorry, a block diagram? So, you know, we could look at it as here's my global input Xn, and here's my global output, which is X1. Like we're trying to find the pickup head output, basically. I could create a relationship of X2. We have that transfer function. So that would be like equation 1 would be that kind of equation. I could create a transfer function pretty easy because it's single input, single output. However, to get to x2, this would be a combination of x1, so some kind of transfer function here. This is a negative feedback loop, so x in goes in, and this would be basically part of equation 2, part of equation 2 going in here. That's one way you can look at it from the block diagram. So some of you from lab 2, instead of doing like an SSR, you did like a block diagram. So if that makes sense to you, right? I have that first equation I can create a transfer function from, but the second equation I can try to, piece this together because it is basically, oh, you know what? No, that would be a positive. Because from there, I have a positive x1 going in and x in. That gives me my output here. We can set up essentially a system of equations to be able to do that. So for example, for this block diagram, 1, the transfer function would be x1 is equal to, here's our transfer function. It would be B1S plus K1 over M1S squared plus B1S plus K1, all times X2. So that would be our first, that would be the transfer function there. X1 is equal to this transfer function times X2. That's what we get from the first equation. I can just rearrange it like that. We could also say this is x1 minus, or sorry, x1 over x2 is what's in the brackets. That's our transfer function. Okay. Now for the other one, for 2, again, I can take this equation right here and we can combine it. So we get m2s squared plus b1 plus b2s plus k1 plus k2 this is x2 is equal to a combination of, we have b2s plus k2 times x in. You know what? That's what I'm missing right here. I should have a transfer function here, basically, that feeds in there. Plus, we have b1s plus k1 times x1. So I can look at it kind of from a block diagram standpoint. This would be right here, b2s plus k2. This would be b1s plus k1. And the combination of those added together then goes through basically this transfer function, which relates to the m2s squared dot dot dot, to solve for x2. But I know that I can't necessarily make a transfer function with that because I have 2 inputs, but I can use the 2 of them using algebra. Now that I'm in the S domain, Laplace, right, I can now substitute one of these in for the other and be able to actually take this complicated system and change it to one that's more simple. X in goes in, and then we have a new transfer function that then spits out x1. Because that's what we really care about. I don't necessarily care about the cart or the chassis. I care about just that pickup head. So we can take this complicated system, either looking at it from the block diagram standpoint or just from an algebraic standpoint, and we can make some substitutions to solve for it. So that's what we're going to do here. I don't really care about x2. That's not something I really care about. So I can take this first equation, we can solve, basically just rearrange this. So we get m1 s squared plus b1s plus k1 over b1s plus k1 times x1. We can plug this into x2. And so once I do that, I'm just going to have x1s and x1. So we're going to move the b1s plus k1 over to the other side. So then from there, we should be able to create a transfer function. So here we go. This becomes m2 s squared plus b1 plus b2 s plus k1 plus k2. This is going to be multiplied by m1 s squared plus b1 s plus k1 over b1 s plus k1. I'm missing an x1. I'll get to that. Because this is just for the left-hand side. Boom, boom. But I also want to bring this over. So we're going to subtract that, but I need to have a common denominator. And so we can just multiply it by itself. So this would be b1s plus k1 squared over b1s plus k1. And this is equal to b2s plus k2 times xn. Okay, so I'm close, not quite there, but I can take, obviously I'm going to do some FOIL here. So we're going to get the fourth order equation from here. We're going to subtract this. That's all over this term. And then I should be able to get to a transfer function where we can relate. Now I have single input, single output. I don't care about x2. We're just combining everything to get that simpler transfer function. Single input, single output. Then we can actually look at vibration frequencies, Bode plots, stuff like that. Questions? It's really, again, Laplace is nice because it allows us to do algebra, but the hard part is that it's algebra, and it's easy to mess up. So taking your time with it, making sure you got all the right positive and negative and moving stuff over and all that. No questions? Keep going. Okay, our goal is to get to the transfer function. Once I have the transfer function, then we're going to plug values in. I like to have it all in terms of variables because if I want to change something, it's really easy to change if I have it in this format. So the next step is to get to the equation, which I have right here. How much is this? that would be the transfer function. So I'm not going to go through all of how I did it. Basically, this on top, this is like the B1S plus K1 times B2S plus K2. That's how we get that numerator. The denominator here is when you FOIL it all out, some of the parts actually cancel out. And so we do have some subtraction. Some of those terms cancel out, and we get our transfer function that looks like this. Good. So what I'd like you to do, once we have this, one thing I don't want you to do is just try solving for each of these terms using a calculator. Now that I have the transfer function, I'm going to set, these are my components. So I want you to put this in MATLAB. Here's my components. Then I want you to take that numerator and create that using variables. So pull from M1, K1, B1, etc. After that, we can actually, MATLAB will, once you run it, tell you what the transfer function is. You can find the roots. Our goal is to find the vibration frequencies. We have to know those numbers to be able to solve for it. This is a fourth order system. So there will be two sets of roots. And then I want you to plot the Bodhi plot. So this is the last thing we're going to do today. We're going to try to plot that Bodhi plot, see what's going on with the system. How does it respond to different frequencies? What are its vibration frequencies? Last thing today. I want to start with this. I'm going to start with the components. Instead of multiplying these asterisks, put stuff in parentheses. But remember, you want to face all this. And again, our goal is to find the vibration frequencies in the Bode plot. Oh, no, no, no. Those numbers, I think it's so here's my code. Again, it's going to save you a lot of headaches. Instead of calculating each term, I can just have in terms of variables, let MATLAB fill that in. And it'll tell you, if it's got problems half the time. Sometimes you may just type in something, it won't catch it, but if you're missing like an asterisk or something, it tells you. So just double check that. Our goal then, hopefully you can plot a Bode plot and solve for vibration frequencies. How do you find the vibration frequency? From a transfer function based on an impulse. How do we find those frequencies? No, that sinusoidal transfer function, that's just based on, again, frequency. This is where you're solving for the roots of the poles of the transfer function. That's how you can find the vibration frequency, which are very close to the natural frequency and resonant frequency. In this case, we should have two peaks, which you should see in your Bode plot, because each mass has its own resonant frequency. I'm going to give you a little bit more time, and then I'll show you, and we'll wrap it up. But Chris got it too. So, okay, let's talk about this. So, this is a little bit complicated to get to, right? I take a couple equations. I can create one transfer function. Now I put it into MATLAB. I let it do all the math, and what it should spit out is something like this. So for the system, this is our transfer function. It's got all the numbers in there. Now, what's nice about this is if I had to change the mass, I mean, let's say this is for the Walkman or whatever. If I have to change the mass of a component, or I can't find that material, so I have to find one with a little bit higher stiffness, instead of having to redo all the numbers. All right, I'm just gonna change one term, and that'll fix it, right? So this is our system equation. It is fourth order, and let's talk about what we're trying to find. Our goal is to find the poles or the roots. This will give us the vibration frequencies, and we're actually going to have two of them. Okay, so we have two sets of roots. So from those two sets of roots, we're going to find our vibration frequencies. Now you can have MATLAB do this. You can use a polynomial root finder on your calculator as well. But the roots of this would be negative 24.9 plus or minus 122.9 I. The other set of roots is negative 25.47 plus or minus 316.1 I. So this is our first vibration frequency. This is our second vibration frequency. This also tells us, like, when I hit it with an impulse, if you remember, the Laplace transform of an impulse is just a constant. So I'm multiplying this transfer function by a constant, and then it's going to die out. And so really the output of this is going to be like e to the negative 24.9 t sine 122.9 t. Similar for the other root. You see it's actually going to die out really fast. Way less than a second. Like a sixth of a second, really. It's going to die out, reach steady state. So we see that it does reach steady state pretty fast, but that frequency based on the impulse is going to be 122.9. And that we can see this kind of on the Bodhi plot too. You probably found, maybe you've looked at some of those peaks. These are going to be similar. Again, they're not exactly the same. Vibration frequency is not the same as natural frequency or resonant frequency unless there's zero damping. That's where they all line up. But we see we have two vibration frequencies. One of them lower, one of them higher. What do you think? I have two vibration frequencies. I have two masses. Which mass relates to which one? The higher the mass, the lower the vibration frequency. Bells. Anyone do a bell choir? Yeah, who's got time for that? The larger the bell, the deeper the vibration frequency, right? So larger bell, lower note. Smaller bell, higher note. And so what we see is this is going to be the larger mass, the X2 or the mass 2. That has a lower vibration frequency because it has more mass to it. Mass 1, the pickup head, is a lot less mass, therefore it's going to have a lot higher vibration frequency. So again, vibration frequency is one thing just based on an impulse. But if I'm looking at the Bodhi plot, this is based on a sinusoidal input. How does my system respond? Well, again, we can look at those two. Basically, I found the peaks, and they're really close to the vibration frequency. So again, the higher mass has a lower resonant frequency. The smaller the mass, the higher the frequency. And so that's 124 for mass 2, then 311 for mass 1. So if this was a different kind of system where I had some kind of sinusoidal input, I could be looking at, how do I avoid those resonant frequencies? I might not want to be at really low frequencies because I still get some amplitude, but if I, can have an input frequency that's a lot higher, I might not see any transmission. Based on that input, magnitude drops pretty quickly after 300. So running this at 400 radians per second, if I had some kind of sinusoidal input, is not really going to affect the system. Based on the mass, spring, and dampers, anything in this range, you don't really see an output. So that's how we can use frequency analysis just to tell us a little bit more about our system. We started the day with what happens if we ran a test with the shaker table. Could we determine some of these components? And then we talked about vibration frequencies and ultimately being able to use MATLAB to do a lot of the work in terms of numbers. Any questions? All right, so this is what we did today. Beyond what I talked about, we also talked about transmissibility. It's the same as magnitude for a mass spring damper system. So how much of this, and we can see that from the Bode plot too. What frequencies are we going to see a sizable output compared to, if I'm running at higher frequencies, I can decrease that amplitude. So that is in terms of displacement as well as force. Next class, we're going to run a lab that involves frequency and stuff. But if we still have some time in the class, if you have any questions, if you got homework stuff, great. If you need to go finish your capstone, I completely understand. But I'm excited to see you tomorrow. And yeah, I'll be around. So thank you for paying attention. This is my last lecture based